Welcome back. In the previous tutorial, we have seen the support vector machines, the theoretical intuition, and in part 13, we have seen naive Bayes classifiers. So we have already trained naive Bayes classifiers using quanteda text models package, and we have predicted text data using title and abstracts from literatures extracted from PubMed literature. We have used the Bayes classifier to predict whether an abstract is COVID or SARS. So we have trained Bayesian classifier, or you may call it naive Bayes classifier, and we have used a model to classify the training and the testing data sets. So in the previous session, we talked about support vector machines. If you haven't already watched this support vector machines theoretical intuition, I recommend to have to watch and come back, or I would also recommend to watch the practical session for Bayes classifier, because that's where I explained our data, and that's where I did the tokenization and the document feature matrix and all the quanteda steps. I have already described it in this part of our previous video. But for now, I would just like to give you a small highlight what kind of data we have. So if you remember, we have used this package dplayer, ggplot to carry it, and bib2df package. bib2df is actually to read our bibtext data. So the bibtext data, as I have explained it in our previous video, is extracted from PubMed literature. So I converted it to bib file, and then once you have the bib file, we have 4 different bib files, which they are for SARS and also for COVID. And then once we read them, we label them. One coded them for COVID if the abstract is about COVID, so we label them as 1. If the abstract is about SARS, we label them as 1. And then we have already done some pre-processing. We have split the data. So once we split the data, we have done tokenization using quanteda. And this is all that we have explained it in the previous tutorial. So once we have done all the tokenization, removing stop words, removing custom stop words, and also removing punctuations, we have already done our tokens. We have identified our tokens. Once you get your tokens, you can change it into document feature matrix. And once you have document feature matrix, you can produce the document feature matrix, but the TF-IDF version. We have also explained what TF-IDF is in our last tutorial in the previous sessions. Just in case you would also want to go TF-IDF, you can. We have one video for it, and you can have a look. So maybe I can give you a little bit of what our data look like. Let me revise. Maybe let me give you some. So the let's say our training data. So if I simply show you the distribution of our training data, so it's like 50% of our training data is COVID, and roughly about 50% is also SARS. So the data we have is a fairly balanced data set. So we don't need to worry about balancing strategies like upsampling or downsampling, which will be a topic for our future sessions. But for now, I will just simply proceed with really a good balanced data. And then if you remember, we have trained naive Bayes. I can simply rerun these models. So if you remember, we have used this text model from quanteda text models package. We have used this function text model NB. What it does is you just need to give it X and the Y variable. The X is all the features we have, all the, when you do the tokenization, we have document feature matrix. And once we have the document feature matrix, we have all the features that we can assign into to X. Then it's simple, so you can simply pass it to text model NB function, and then you have your model. Once you get your model, you can use that model to train, because it's already trained. You can use it for prediction. But before prediction, if you remember, we have used this DFA match, and this is because the features when the test data document feature matrix and then trained document feature matrix, they were different. So if you remember, let me show you in the fit. Actually, I can simply show you dim train DFM. Should be train DFM. Maybe train DFMAT. So that would be something like this. So, and then if we go, so it has this kind of dimension. But if we do the same for test, so it has a different dimension. Test document feature matrix. So it will be, you see, it has different dimensions. So our algorithm is trained by this number of features. That means more than 11,000 features. So our training algorithm is trained by this number of features and this number of observations. But what matters most is the number of features, the number and the type of features. But in our test data frame, we only have 7,000 features, and this actually may differ, in type. Let's say a term that's presented, in this document feature matrix, in our trained data feature matrix, may not be present in our test data frame matrix. So that's why we have to match them. Otherwise, with this, you can match. This function will create 0 cells, or if there are features that are not part of the training features, it will remove them, and it will make exactly identical number of features. So if you remember, we can also do this. So it should be, this is a test data frame, but it is matched with a training data set in terms of number of features, number and type of features, actually, type and the number of features. So we can do the same and see this would be exactly like the training data set. So this should be, so you see 11,000. So now you can easily use it for prediction. For prediction, we use the predict function, then we pass our model, and then we give it the new data, which is the new the matched data frame. Then once you have that, you can simply use caret package to bring your confusion matrix and 2x2 table, and finally you can have everything about sensitivity, specificity, and the like. So we have already done that in the previous session. So for today, I will just proceed directly using this. So I will train 2 models, one using document feature matrix and another one using DFA using the DFA value. Then once we have that, we can simply compare the results between this is naive Bayes with without TF-IDF, and this one is naive Bayes with TF-IDF. Then we will have SVM model, simply SVM. Let's say SVM1, let's give it SVM1, and then the other one we call it SVM TF-IDF. You can call it like that. So to train SVM model, we have already seen text model NB. So to train naive Bayes, we can simply use text model again. So this text model, they have multiple functions. So these are for LSA, for latent semantic analysis, naive Bayes, support vector machine, and word fish modeling also. And you can do lots of many different, depending on supervised on or unsupervised learning. So what we want is SVM algorithm. We are not going to use SVM linear because this is they just added, it's a new function. I think it's not complete. It's under development, so we are not going to use this one. So we are applying linear kernel. So SVM from quanteda text model, it uses the linear kernel. It doesn't have any other kernel strategies. It's mainly used. It's mainly done using the linear kernel. Actually, as I said in my previous video, text data is actually linearly separable. So this might work very well. So but we will see. Let's see what do we need when we write our text model. I think the first thing we need is X data, and that's our data frame. The X features, and that's train DFA matrix. All the training features, we need them for training our data, and then the Y would be the dependent variable, which is train include. That's all dependent variable. But we don't. Maybe we need any other. Otherwise, we can also simply keep it as default. But let's see what else do we need. So the X and Y, we already defined them. The weights, these are you can kind of define depending on your kernel strategy. They say, let's say we are using liblinear, which is a linear kernel, and they say the default is uniform, uses default. So and then dog freak, that is, it's weighting strategy by number of training examples, and term frequency is by the relative size of the term frequency. I think that's how it's calculated. But to have a better understanding, I would advise to look at the detailed vignettes of the package. But otherwise, we don't need anything. So we just simply define the weight. We can also ignore it because it's a default. But otherwise, you can also simply do it that way. So that's how we train our SVM model. This is just without the TF-IDF data frame. Now we have trained our SVM model. So it's still training, but it's quick. It's very quick. So it doesn't take much time. It's about a few seconds. And now we want to train the TF-IDF version of our model. So we just replace our data frame. It's the TF-IDF version of our data document feature matrix. The rest would be identical. So we just define the Y is the same. We are not changing it into TF-IDF or something. It is a dependent variable, but all the features that we are using the TF-IDF version of our data. So let me run this again. So now we already have 2 models. one using simply using the simple frequency. Simple frequency in a sense, words are simply counted in numbers, but they are not weighted. But in TF-IDF, the model is trained using the TF-IDF version of the data, which the words are weighted according to their numerical, according to their TF-IDF values. So we have already discussed TF-IDF, and you can probably look up, revise our videos. So the next thing, once you train the model, is you use it for prediction. So we will use it for prediction. Let's say we can predict one class of our model. Let's say using the first one, the SVM one. So and then what you need in prediction is let's call it our predict class. Let's call it predict class. And then what we need is predict function. So once you say predict function, you define. So we define our model. Our model is SVM1, and then after that, you can give your data. So let's say you can call this one model equals SVM1. Our new data is DFA match. The one we have matched, the matched data frame, matched document feature matrix. That's what we need. That's all. We don't need anything else. So it's already done. So we can simply run it. Argument object is missing. Maybe something is, we can ignore this one. Maybe the predict function is wrong. So we just simply give it object. So it's a model object, and then so it doesn't require this model object, or we can simply give it object or something. But what you can do is simply you give your model, and then after that you give the data. Now it should work if I run this. Now it's working. So we already have our predict class. We can have a look if you want predict class. So now we can run this. So you see 150 of them, 150 of our half of the data is almost assigned. But let's see how the table look like for the test data. Test how they are labeled. So this is 152 were COVID and 141 were SARS. But our model is saying 152 are COVID, 143 are SARS. We will see which of the two. It seems two of them are moved to this. So there is some kind of misclassification here. A tiny proportion of the total is misclassified, but we will see which of them are misclassified. So once you have that, the next thing so this shows your our table. But the next thing is we need to do contingency table, or you can call it confusion matrix. Confusion matrix is a matrix for, I don't know, confusion or something. I think it's a matrix because it's in a 2x2 table. If your class is binary category, so you have a 2x2 table. And that what you have when you create your table. Usually the predicted class comes first, and then the actual class comes second. So we have predict class. Then after that we can take the actual. Our actual is test include. That's our actual labels. Now if we do this, we can have our confusion matrix. So this is how it looks like. So you see from these are the actual labels, and these are the predictions. So that means from 152 COVID papers, 142 were correctly classified, and then from 141 SARS papers, 133 of them were correctly classified as SARS. But there is some misclassification. 10 and 18 of the total were misclassified. And with that, you can calculate your sensitivity, specificity, and you can even calculate manually using the formulas of sensitivity, specificity, predictive value positive, negative, predictive value positive, precision, and there are many other ways of many other metrics that you can calculate. But we are not going to go into manually calculating them. We can just use the already existing function, which is already there for us. We can use the Caret confusion matrix from the Caret package, and we will be fine with that. So let me save this data. So this is our contingency table. Let me call it contingency table, and let me just contingency. Okay, contingency. Or confmat. Let me call it confmat. I already have that, but confmat SVM. Let me call it confmat SVM. So so now I already have on my confmat SVM. The next thing I need to do is I need to use Caret confusion matrix. Caret confusion matrix now. So it will give me everything. So what I do is I can use maybe I should call this one table. Actually it's better, contingency table. So I call it contingency table, and then let me call this one conf.mat SVM. And then I can use simply confusion matrix function. The confusion, as always, you can simply copy this, and maybe you can have a look what it means. So the confusion matrix function from the caret requires this seems to be a bit much. We are not going to go through all of this, so it's better let me run it again. Yeah, model matrix library, because I have two different but what I want is from this one, the one from caret, but it's giving, I don't want to do all of this. So what you can do is you can call your confusion matrix table, or you can simply call all of these, and then you can put it here. So I'm using the cont table, and then if I simply run this, I can show you there will be some still it works, but there will be some values that you may be interested in finding. So this gives us the accuracy 95. I mean, it gives us a contingency table itself. It printed the contingency table, and then it gives you the accuracy, and then the 95 confidence interval, of course, for the accuracy, and the kappa value, percent agreement, and then it may give you some p-value for it, and it gives you sensitivity, which is quite impressive for this model, and specificity of 94%, and positive predictive value of almost 95%, negative predictive value of 93%. And another one you may be interested in is like F1 measure, or what else? F1 measure and precision. Precision is actually one of the important metrics that you may be interested in. But with this, it's not being printed out, so you can add one additional function, additional argument, which is mod equals everything. So then everything will be printed out. So if we run this and we rerun the previous one, so now we should have everything. So we now have F1 measure, and we also have balanced accuracy, and we have precision. So in my previous video on bias classification, if you remember, I said ideally, if your classification algorithm is working well, the precision should be kind of much higher than the prevalence value. So we have the prevalence is 52%. That means the number of cases, COVID cases. Number of COVID papers was about 52%, but our precision is precisely telling us 95% of them, which is quite impressive. Yeah. So this is we have done conf.mat SVM. So now what is left is for the TF-IDF function. For the TF-IDF. We already trained our model. So the next thing is we simply predict our TF-IDF test data using the TF-IDF model of our algorithm. Yes, TF-IDF. So what we can say is we already have SVM TF-IDF. Let me call this one TF-IDF. Then we give it the TF-IDF version of the data. Now you can simply run it. Now it's already done. It's quick. Then once you have that, what you can do is we can create again contingency table. So we can create our contingency table, but the TF-IDF contingency table. And then what you can do is simply pass the table function with a pred class. As I said, the prediction, the predict should be on the first part, and then the actual level should be on the second one. Then you can have the table that we have here. Now let's run this. After that, you can simply call your confusion matrix function from caret. Let me call this conf.mat SVM TF-IDF. Then after that, you can, as I said, you can simply confusion matrix function, and then once you have that, you can call your contingency table. Our contingency table is this one, the one we just did. Actually, this one here. And then we can define the mod. Mod will be everything, because we want to print out everything, including sensitivity, specificity, or precision, or whatever. Then you can run this, and let's see. Now if we run this, so you see now this model seems to be a little bit weaker than the previous one, because the previous one, if you remember, we have 94% accuracy. Yeah, 94% accuracy and a sensitivity of say 93% and a specificity of 94%, and precision level is 95%. But this model is telling us sensitivity is 92%, it's almost 1% down, and specificity is 2%, 92%, almost 2% lower than the previous model. But still, it's quite impressive. The precision is also high, but still lower than what we had in the previous, which was almost actually 95%, if you remember. So that means in the models that we train now, the simple frequency version of our data seems to be a better option, because the other, it seems it's more accurate, it's more sensitive, and more specific than the DFA version of our model. I mean, you can kind of compare them, like creating a table in a long table, and you can see you can have side-by-side comparison. For that, what you can do is simply you can check what are the names of this. So you can see the first one is positive table overall by class mode dots, let's say. So if you simply call conf.mat table, so it will print your table. But if you say okay, let's say by class, so it gives you some of these values. So then you can kind of let's say, if I want, I can also round them, let's say round, and then how many into significant digits, so 3, and you can have all the values in this kind of digits. But you can also later on you can pick all of them and put them in a table, like, you know, one row would be about naive Bayes, second row would be about well, I don't know, naive Bayes DFA, third row will be about SVM, and fourth row about SVM DFA. We will extract them later in our future tutorial. We will collect all of these models and all the predictions, and afterwards we can have an easy way of comparing this. But if you remember, we already have conf.mat. This is for the naive Bayes. So for the naive Bayes, if we compare naive Bayes with naive Bayes DFA, again, the naive Bayes without the DFA version of the data seems to be working. I mean, seems to be a good model instead. So we have 90%, and then here 90%. But if we use DFA, that means it's giving you sensitivity of 86% and a specificity of 87%. The accuracy is also not bad, 87%, but it didn't beat the one we got using the simple frequency model, or without the DFA version. Again, for the SVM, if you remember, we have two models. One was SVM. So if we print this, and we already have 93%, nearly 94% accuracy, and the sensitivity is 93%, and the specificity 94%, and then precision is almost 95%. So it seems to be quite impressive again. But if we print this one again, then we see this model is again at least this one achieves better than the DFA version of the model. But so far we have 4 models. So our model, the one we trained using SVM function, using SVM algorithm, using the simple frequency, and that means simply counting the number of words and creating our document feature matrix. And that model, the model created by that, using that data, using that document feature matrix data, seems to be performing way better than the others. Yeah. So in the future, this is how you do it in using quanteda models. It's super fast. It's very fast, and it's yeah. I think one of the big advantages of quanteda models package is it's the speed. But you don't have much control with it. You cannot tune it. So it's giving you the way you train it. It's like you simply use this text model SVM. You can give any X and Y. You don't know how the cost and gamma and all these optimization parameters are tuned in the model. Everything that's happening behind this function. Let's say just wanted to see how this function is written, but I still don't have access. I mean, yeah, you see XY model, you see some, this is how it's written, but again, maybe, no, I don't have access to it. So we need to go to the details to find out how this model is written and how this package has written it into at least the gamma, the cost, and other values for the SVM algorithm. Otherwise, it's working very well, so it's fast, especially if you are working in a situation where you don't have much resource, where you don't have you know, the bigger RAM or something. This is a good choice to do. Yeah, text classification. At least you can use it for using a small computer. I mean, you don't need a powerful device to run using this text model package. Otherwise, if you want to run E1071, then you have a direct control. You can assign multiple values for cos and gamma values, and you will be able to fine tune your algorithm and maybe find an optimum hyperplane. Yeah. So in the next session, in the next tutorial, I will go into I will train SVM algorithm using E1071 package. We will try different kernel strategies using polynomial, sigmoid, linear, and radial basis function, and we see how it works compared to the quanteda text models SVM algorithms that we are just seeing. Yeah, that's how you can do it using SVM quanteda. But otherwise, it's quite easy. Yeah. That's all. Thank you very much, and stay tuned.